Thank you for this opportunity to present our work in this conference. So the work I'll going to present exploring the impact of extra dimensions on the equation of state of baryonic matter and the structure of the neutron stars. So this work has been collaborated with Professor Manjari Bakshi from IMSC and Professor Shomista Bonik from BITS Hyderabad. So let us start before jumping into what we have actually done. So let us discuss some how higher dimensionality actually come in the literature. So you can see there are many theoretical considerations that actually supports existence of extra spatial dimension, and other than that there is string theory who are actually consider higher dimension like 10 or more dimensions, and later to solve other problems like gauge hierarchy problems, and so people are actually revisited the higher dimensional model to resolve it. And even there are some high energy dark energy or dark matter model that actually supports the aspect of the higher dimensionality to explain those things. So it is exciting that recently in the gravitational wave direction of GW170817, it has been observed that there is, so this is the only gravitational wave detection where the both gravitational wave and electromagnetic counterpart has been detected, and it has been found that the luminosity distance from the same event is actually difference when you are observing from gravitational wave perspective and electromagnetic wave perspective, and you can actually see the error bar. If you consider the higher error bar, so it is really high difference because it is in megaparsec thing. And later actually many theoretical paper actually came to study those things in the perspective of higher dimensionality, and they are actually trying to say that gravitational wave actually leaking into the higher dimensional aspects, and those why they are actually getting the low gravitational wave strain, and the calculation of the that strain is not through the calculation of the strain, the luminosity distance is not actually correct. So they actually came up with higher dimensionality in that picture. And later LIGO and like Varga also themselves also studied these things, and they showed in their paper that this aspect of higher dimensionality cannot be actually ruled out. So this thing is actually exciting for us. So being Newton star people, if Newton star is the best laboratory to study such natural phenomena, so we actually jumped into the picture and tried to see what higher dimensionality will affect how they will affect the Newton star, any structure or equation state or something. So who actually attended last day's Professor Ritam Mallik's lecture, they actually know what the Newton star. I am not going to repeat that, but can tell you what is the MR curve. So if you have a Newton star, so from the Einstein field equation, if you consider spherical symmetric metric line element to define the interior space time, from there actually solving the Einstein field equation, you can get two kind of equation, that is mass balance equation and the force balance equations. So those are basically TOB equation, and solving them using the equation of state, which for this case we have actually considered density dependent equation of state model to signify the strong interaction inside the Newton star. You can actually get this mass radius curve. So if you know the mass, so mass you know from the observation or so, and you can actually predict the radius. So that how actually mass radius equation helps you. So what we did in this work, we try to actually study the Newton star completely in the higher dimensional framework, and we try to construct the equation state where higher dimensionality effect of higher dimensionality is there. So we took a density dependent equation state already there and try to construct it putting the effect of the higher dimensionality. And finally once the model is there, we also try to test its physical acceptability and stability. So you can easily think like this. So we have a d-dimensional Einstein-Hilbert action. Then we we have derived the d-dimensional Einstein field equation where Einstein constant is not known. Then use d-dimensional weak gravity limit to determine this Einstein constant. Then use d-dimensional spherically symmetric line element for interior space-time. Evaluated the vacuum solution for exterior solution for the d-dimensional space-time. Then we have come up with the mass balance equation and the force balance equation, that is the TOB equation. Then we have extended the density dependent model for the d-dimensional space time, and finally we achieved the mass radius relation here. Once we have achieved, so we try to test its physical validity with the modified Boosdal limit, which is applicable for d-dimension equation, and finally we have tested the model if it is stable against the radial pulsation in the d-dimensional case. So it seems like life is pretty easy if you follow these steps, but it actually no. So why no? Because you don't know the value of the gravitational constant in d dimension, and or either way you don't know the what is the value of Planck length. So there we actually following this Back's this very good book. Following that, we took this formalism. They have actually show what is there is a relation between the high dimensional gravitational constant, and so there is no point of considering that the gravitational constant is same throughout the all high dimensional spaces. So following their work, we actually took this formalism where LC is the length of the extra compact dimension, and it depends on the different dimension based on this power d minus 4. So as I said, we took the Einstein-Hilbert action, then solved two Einstein field equation in equation number 2. Area of the unit sphere you can see 3. Generally for the 4-dimensional case it is 4 pi. For the other dimension it will change. And we use the usual trace energy tensor for isotropic fluid we have considered here. Finally, you reached in the equation number 5 the Einstein field equation. So we have solved the exterior Schwarzschild spacetime metric for d-dimensional based on the vacuum solution. You can see the mass balance equation and force balance equation in the equation number 8, and this is the basically TOV equation number 8. We did some scaling for our for convenience, and we have used the natural like we consider G 4-dimensional G is 1 and C is 1 for simplicity. So here we started like extending the effect of higher dimensionality on the relativistic mean field. On the density dependent equation of state. So we have like 3 equation of field equation for the missions. So by considering the mean Lagrangian, using that solving the Euler-Lagrangian equation, we have this equation for the missions. Then we have equation for the baryonic equation of field equation and the leptonic field equation. Solving all those things, we can actually come into the equation number 19 and 20, where we have applied the relativistic mean field theory. And there I am actually showing in the equation number 18 a rearrangement term. So there actually all the G's are actually the coupling constant where Mason couples, Mason and baryon couples. So here, okay, one thing I need to say here, we have used sigma, omega, and rho Mason. So iso sigma Mason, iso vector omega Mason, and iso vector rho Masons. So solving all those field equation, we able to get the value of rho and p. And since here the coupling constant G's are not the constant, it is density dependent. We took the functional from given by Type et al. And used the respective this fitting parameters value, this ABC on those things from the Type et al.'s work. And using all this, we can actually come to the equation of states. So the extreme right side is left side is basically equation state for the different dimensional value, where we have actually computed this xi value. So we get trouble in computing xi value because any xi value actually not giving the solution of the TOV equation. So we get hard time to find for which like range of value we are actually getting the solution of the TOV equation and MR curve. So by that way this xi value is defined. So in the like middle and right end plot, you can actually see the how equation of state is actually changing with the changing of xi value. So one interesting thing in the rhythm the stock, if you have seen the gravitational from the result of the gravitational wave, the bound they are giving for the 1.4 solar mass, they are actually favoring the softer equation state. However, the Nizer or Prex, they are actually preferring the stiffer equation state. So there is a dichotomy. So it is interesting to see. You can see that thing here also for the higher dimensional cases. For the lower dimensional, for the lower density, those are actually softer, but for the higher density, they are actually stiffer. So it is a interesting phenomena we found here. So we found finally the mass radius curve. Although we have plotted all the dimension MR curve for different dimension, but from the unit of the mass you can understand it is a apple to orange comparison. But for the posterity we have just shown in a same curve, same plot. So I'll going to say how we can actually compare. So here you can see for the 5 dimension and 6 dimension, we are actually when the xi value is increasing, the value of the mass is actually increasing. And so question could be like this: why we are only showing 5 and 6? Because beyond 6 we are not getting any maximum mass value. So that's why we limited our study up to 5 and 6 higher dimensionality cases. So then we have tested the Bushdal limit for this, and this is the Bushdal limit for d-dimensional space-time, and we are way within that limit, and we can say that our solution is physically correct. Then it is important to test the stability of the model against the radial pulsation thing, and you can see that the fundamental modes are like greater the square of the fundamental frequency of the fundamental modes are greater than 0, which actually tells that our model is actually stable. So by the stability criteria, we have tested that our model is actually stable. And here we have shown some numerical value. You can see how the higher dimensionality we are getting actually the maximum mass. So here is the last column. It is now we have take the compactification, and so what is that? We are taking the projection of that mass in our 4 dimension. So you can see as the higher dimension is increasing, we can actually explain the higher mass neutron stars. So, based on the recent detection of the higher massive neutron star, we can actually tell about those mass gap, and so based on these higher dimensional theories. So, and here all the density and pressures are also compactified. That means those are projected in the 4 dimension cases. So, this is completely projected profile. Here we are showing those data. So, what are the important takeaway? Important takeaway is we able to construct a Newton star model completely in high dimensional framework. For the first time, we able to show the effect of the high dimensionality on the equation state. No other studies has been shown that, and we finally tested all those things like the physical, acceptability of our model and the stability of the model. We have checked. Now, next in the coming few time, we also try to check the observational signature of through our model, or try to constrain those based on the observational signatures. So that can be done in the next few years or so. So thank you, and thanks to Mr. Christopher Nolan, you can see the projection of the 5 dimension here.
You are using the equation of state higher dimensions, right?
No, so yeah, so we are taking like equation of state density dependent there. So all the aspect where the space time is there, we like updated to the high dimensional.
But then in the higher dimensions, you will have larger number of terms because you should have tensor particles and all. Because the tensor particle in 5D will be like a vector or pseudo vector in 4D. So
Okay, so here our approach was the simplistic as I say, sigma omega rho that model. So those complex
that is true in 4D. That I know. But then in higher dimensions, there will be more because if you compactify, tensors in 5 dimension will become vectors. Additional terms will come up. So do you take into account those extra terms in the 5 dimension or when you go to higher dimension? To see, well, I mean, so this simple we can get at least anything stable in like we tried to do it very generic means d as a free parameter increasing the number. So in higher dimension means in the GR aspect we are not getting any stable. So with 5 and 6 we are with simple model we are getting some stable situation. Now we'll investigate more on the particle physics aspect that to what are the modification we need to do there. Yeah, one more question. Is higher dimension sensory is that
no, they should not be, but whatever equation state we generally study, they are in the Minkowski space, right? So yeah,
extra dimensions are flat.
yeah, for that way, yeah.
So what is the size of extra dimension you consider?
Okay, so we have run. So as I said, we are not.
For one extra dimensions is excluded from solar system observations entirely.
Okay, what is that?
So it should be astronomical units that's excluded. One extra dimension in ADD model.
So you are telling about the large extra dimensions, right?
You said it's flat, so it is large.
Yes.
You said they're flat, so there must be.
So I am saying that whatever the equation state you are like deriving, all are in the laboratory frame. So that should be also in the curved space time, if you trying to say so. So these higher dimensions we are trying to say, those are curved space time, not flat space time. As a gravity perspective, those should not be like flat, because we are studying inside the higher dimension, like in Newton star.
No, but what is the size of the extra dimension?
That I am showing here. So from the xi, as I showed, you can see that xi is basically lower extra dimension. It is not the larger extra dimension. So xi is basically g d by g, and from the g you can go to the Planck length. So you can understand, if it is 10 to the minus 15, so LC value is 10 to the minus 15, so Planck length will be smaller compared to the 4-dimensional Planck length. So it is the smaller extra dimension, not the larger one. ADD model tells about that.
So there is a limit of micrometers for 2 extra dimensions.
So our will be less than that, and we are not considering it. From the solution we are getting this. As I said, during the solution of the TUV equation, these kind of values are supporting the solution of the Newton star model, and whenever we are getting this solution, so this xi is basically gravitational constant in the 5 dimension by gravitational constant in the 4 dimension, and from the gravitational constant you can actually link with the Planck length, and whenever you go to the Planck length, because the this 10 to the minus 15 value, it will be less compared to our Planck length value.
No, that I understand. Maybe we can talk later.
Sure.
One more question.
Yeah.
So you build a neutron star in 3 plus 1 dimension.
3 plus 1 spatial dimension.
No, 3 spatial plus 1 timeline in
4, yeah.
in 4. But then at what point of time do neutrons start probing extra dimension?
What no, so
what density? I mean, they must all be
so it is not like based on any density. I am saying, if higher density is there, it will be forever for there. We are not getting the signature. Like, we are seeing everything in 4 dimension. Say there 5 or 6 dimension is there. There this study comes in, because we are not getting those signature sitting in the 4 dimensions. So it is not density dependent thing, the higher dimension.
but you take a bunch of neutrons, more and more neutrons in a fixed volume, you will get a neutron star.
Yeah.
So at what point of time, or how many particles you need to add such that neutrons pop into extra dimension?
No, I am looking not like that way. I am saying that whenever initially you are starting, you are sitting in the higher dimension.
I think there is starting. He doesn't have suddenly.
Suddenly the higher dimension is not popping out. Yes.
Oh, hi. So, in the very first slide, you showed some numbers in megaparsec.
Yeah. Yes.
Could you please comment on the errors on those numbers?
Comment of the errors, like how these errors came.
So the first number, which is for the gravitational waves, is 40 plus 8 and minus 14. That's a very large range.
Yes.
The second one is plus 2.4 minus 2.4.
Yes.
So it seems as if the EM thing is completely within the error range of the first one.
So those are calculated by like zero luminosity. All those things are calculated by those guys, like LIGO and Virgo guys. So I could not comment much about them, but I can clearly see that there is a difference in the luminosity distance, and then different studies actually showed that
the central rested values are different, but it seems as if the allowed range is quite.
Are we with an error bar because the errors are?
yes,